So let's keep working through Chapter 5, Exponential and Logarithmic Functions. This section, 5.6, is not hugely different than the one that came before it. Okay, so again, it's logarithmic and exponential equations. We're just combining logarithms and exponential bits into sort of similar problems, and we just want to be able to solve equations involving these things. So remember that we have this definition of logarithms. This is how you convert between logarithms and exponential expressions. Base to this number equals that input. Okay, a to the y equals x. And remember, our bases always have to be positive, but not 1. And we also know that logarithms are 1-to-1, so if you got out the same thing from inputting m or n, you must have inputted the same thing. So for example, 4 times the log base 6 of x equals the log base 6 of 16. So x has to be positive. This is an important thing to point out. Okay, we'll see why. But I'm plugging it into a logarithmic function, so x cannot be negative and it can't be 0. Each log has the same base, so we'll use properties of logarithms to simplify our way towards a solution. Specifically, the power rule there. We'll bring in that factor 4, but now I have log base 6 of something equals log base 6 of something else. And logarithms are 1-to-1, which means those inputs, x fourth and 16, are the same. So x to the 4th must be 16, has two solutions, 2 and -2. But remember, because we started off by plugging x into a logarithm, -2 is not actually an allowable solution. So this comes up a lot on midterm problems. Okay, there will almost always be a problem set up where it makes you think there are several solutions, but from the original way it was written, some of them, or maybe even all of them, aren't actually legitimate. Okay, so in this example, if you had just started the problem here, you'd think, two solutions, 2 and -2. But the original formulation did not allow for negative numbers, so the only answer was x equals 2. So we can check this by plugging into, and this is really just a matter of repeating the work we just did. Yes, 2 to the 4th is 16. Okay, how about this? The logarithm base 20 of x plus 9 plus the logarithm base 20 of x plus 1 equals 1. And this could be just taken straight out of the midterm as a 5 points out of the 100 total type of problem. This is the sort of thing that once you get comfortable doing it, should take you all of, I don't know, a minute. But notice they have the same base, so what can you do with those two logarithms on the left? Well, we can observe, by the way, from the domain that x plus 9 and x plus 1 both have to be positive. So x has to be bigger than -9. It also has to be bigger than 1. There's some redundancy there. Anything that happens to be bigger than -1 will automatically be bigger than -9. So the two conditions together, I must be bigger than -9, but I also must be bigger than 1, is really equivalent to the single condition, x needs to be bigger than -1. This will vary from problem to problem whether the two conditions are redundant or not. But in this example, we really only needed x to be bigger than -1. So let's work with these logarithms. So first, we're going to use that sum property to express the log base 20 of x plus 9 plus the log base 20 of x plus 1 as the log base 20 of the product. But now let's convert it to an exponential. So that input of x plus 9 times x plus 1 must be equal to 20 to the 1st, which is 20. Now if I expand out that product on the left, x squared plus 10x plus 9 equals 20. And now I've got a nice quadratic, which I can use the quadratic formula, or we can factor. This one happens to factor, which means either x is -11 or x equals 1. But remember the original restrictions. X has to be bigger than -1. Therefore, -11 is not actually a solution. What happens, by the way, is that -11 is actually perfectly okay here. If you put x equals -11, you'll get a -2 and a -10, which individually would be bad. But the product of -2 times -10 is +20, and I can take the logarithm of +20. So it was going from this step to this step that introduced some potential problems involving the domain of the functions, which is why you always start the problem by asking, wait, what values of x could possibly work? What is the domain of the function I'm looking at? Okay, so try this one. The natural log of x plus the natural log of x minus 1 must be equal to the natural log of x plus 15. Start by asking what's the domain of each piece, so what's the domain of the equation overall, and then use properties of logs to try to get to an answer. Go ahead. So hopefully we've given it a shot. So the domain of the first term, log x, is that x is positive. The domain of the second one is that x needs to be bigger than 1. And the domain of the last one is that x needs to be bigger than negative 15. So my three requirements are bigger than 0, bigger than 1, bigger than negative 15. That can be summarized as just, oh, you have to be bigger than 1, in which case the other two will automatically happen as well. Now let's use log properties. So the log of x plus the log of x minus 1, we combine into a single logarithm. Now I have the log of something equals the log of something else, and they both have the same base. They're both natural logs, so I can drop the logarithms. Okay, so now I have x minus 1 equals x plus 15. Expand that out on the left, turn it into a nice quadratic, factor, or use the quadratic formula if you can't quite see how to factor it. That suggests two solutions, 5 and negative 3, but remember, x has to be bigger than 1, so negative 3 is not really a solution. Okay, all of these examples have some solutions that work and some don't, so that you get used to seeing both possibilities. Sometimes both solutions might be fine, or maybe both of them need to be thrown out. Okay, so don't just assume certain things always get thrown out and certain things don't. Just check them every time. Okay, so that's it for this nice little quick video. We'll come back at the end and work with similar things involving exponential equations rather than logarithmic ones.